Imagine standing at the edge of the runway, watching a fully loaded commercial airplane taxi with barely a hum from its engines. The ground beneath your feet is alive with invisible energy, bending magnetic fields and resonating with power you can't see but can feel. This is not science fiction. It's a vision that Maxwell Chikumbutso has been quietly working to make a reality. For decades, aviation has relied on fuel, batteries, or hybrid systems to lift tons of metal into the sky. But what if the energy required to fly a commercial jet didn't come from tanks of kerosene or massive battery packs at all? What if the runway itself could beam power directly to the plane as it taxied, lifted off, and soared into the stratosphere? Maxwell Chikumbutso, a Zimbabwean inventor known for his work in self-powered vehicles and wireless energy, may have unlocked a pathway to do exactly that. At the core of this idea is a Mammoth RF radio frequency field engineered to transmit energy over large distances with unprecedented efficiency. Imagine a network of superconducting coils buried beneath every inch of the runway, carefully calibrated to produce a uniform, massive electromagnetic field. This field isn't just a static force. It's dynamic, adaptive, and capable of delivering concentrated energy bursts to a moving target, in this case, an airplane. The concept seems almost impossible when you consider the scale of a modern airliner and the power demands it requires. A Boeing 747, fully loaded, can demand tens of megawatts just to take off, a number that dwarfs even the largest terrestrial power plants feeding a single building. Yet, Chikumbutso's approach leverages principles of resonance and field amplification to effectively push energy rather than simply supply it. It's akin to plucking a string on a musical instrument in one location and having the vibration grow stronger at the other end without physically touching it. The runway itself acts as both the conductor and the amplifier, converting conventional electricity into a directed RF wave capable of interacting with specialized onboard receivers. These receivers, embedded within the airplane, are designed to absorb and convert the RF energy into usable electrical power for engines, avionics, and environmental systems. Unlike conventional wireless charging, which struggles with distance and efficiency, this system relies on a phenomenon Chikumbutso calls resonant energy coherence. By carefully synchronizing the frequency, amplitude, and phase of the RF field, energy can be made to travel farther and with less loss than any wireless system ever attempted. In essence, the airplane is no longer carrying its fuel in tanks but drawing it invisibly from the runway beneath its wheels. During taxiing, the engines can operate at minimal output, relying primarily on this transmitted energy to rotate the wheels and power auxiliary systems. As the plane begins its takeoff roll, the RF field intensifies, synchronizing with the onboard receivers to gradually supply the additional megawatts required to achieve lift. By the time the aircraft leaves the runway, it has been powered almost entirely by energy extracted from the field below. This is more than just a fuel-saving idea. It fundamentally changes the economics and environmental impact of aviation. Runways could become energy hubs, supplying multiple aircraft simultaneously with clean, wireless power. Airports, long criticized for their massive carbon footprints, could become net-zero energy environments by integrating this technology. The vision doesn't stop at small-scale experimentation. Chikumbutso imagines full-scale implementation capable of powering long-haul flights without ever touching fossil fuels. Of course, transmitting tens of megawatts wirelessly is no trivial engineering challenge. At these levels, electromagnetic fields can induce unwanted currents in nearby infrastructure, posing safety and interference risks. Chikumbutso's team addresses this by precisely shaping the RF field with phased arrays, ensuring energy is focused only where it's needed. This is reminiscent of how radar systems focus waves to detect distant objects, but in reverse, the plane becomes the receiver of energy rather than the reflector of a signal. The efficiency of the system depends on the precise alignment of the transmitting field and the airplane's receivers, which must adapt in real time to changes in speed, altitude, and atmospheric conditions. Advanced AI and predictive algorithms continuously modulate the RF field to maintain resonance as the plane accelerates and climbs. This requires a level of computational control that borders on real-time physics modeling, where every electron in the system must be accounted for. In testing scenarios, small-scale models have already demonstrated the potential to wirelessly lift drones and experimental aircraft using similar principles. Scaling this up to commercial airliners is a massive engineering leap, but Chikumbutso believes the physics are sound, and the remaining challenges are mostly practical. He envisions a world where airports are no longer constrained by fuel supply chains or the limitations of onboard energy storage. Instead, the runway itself becomes a living infrastructure, capable of powering multiple aircraft simultaneously, day and night, rain or shine. This also opens the door to redefining aircraft design, as heavy fuel tanks and backup systems can be drastically reduced or eliminated. Planes could be lighter, more aerodynamic, and optimized for efficiency rather than fuel carriage. The environmental implications are staggering. A single long-haul flight could eliminate thousands of gallons of jet fuel, dramatically reducing carbon emissions. Additionally, noise pollution from traditional engines during takeoff and landing could be minimized if aircraft rely more on onboard electric motors powered by the RF field. This could transform urban airports, where communities have long suffered from the loud roar of departing planes. Chikumbutso's vision isn't merely theoretical. Prototypes of the technology have already been tested with smaller vehicles and even boats, showing that large-scale wireless energy transfer is feasible. By embedding superconducting coils beneath roads and waterways, entire transport networks could be energized without traditional fuel or charging stations. Applying this to aviation, however, is exponentially more complex due to the scale and safety requirements of commercial flight. The materials used in the runway coils must withstand enormous electrical loads without overheating or degrading. Similarly, the airplane's receivers must handle megawatts of incoming power without risking onboard electronics or passengers. Chikumbutso's team has reportedly developed advanced metamaterials that can channel high-power RF waves safely and efficiently. These materials act as both antennas and converters, ensuring minimal energy loss during transmission. Even with these breakthroughs, regulatory hurdles remain formidable. Aviation authorities worldwide would need to certify that wireless power transfer is safe for passengers, crew, and other nearby aircraft. Electromagnetic interference, health concerns, and cybersecurity of the transmission system are all issues that must be addressed before widespread adoption. Despite these challenges, the potential rewards are too great to ignore. Airlines could dramatically cut operating costs by eliminating fuel purchases and reducing engine maintenance associated with combustion engines. Passengers might enjoy quieter, cleaner flights with potentially lower ticket prices due to reduced operational overhead. Airports could reduce their carbon footprint and become self-sufficient energy hubs, integrating solar, wind, and RF field storage for continuous operation. The concept also opens new possibilities for intercontinental travel. With energy sourced directly from the runway and supplemented by wireless energy relays mid-flight, airplanes could theoretically fly longer distances without refueling. This could eliminate the need for certain stopovers, making air travel faster, more efficient, and less costly. From an engineering standpoint, the system requires tight integration between airport infrastructure, airplane design, and real-time energy management software. The runway must detect the weight, speed, and orientation of each aircraft to deliver energy efficiently. Meanwhile, the plane's receivers must communicate back to the field to optimize energy capture during every phase of takeoff and climb. Chikumbutso likens the process to a ballet of electrons and fields, where precise timing ensures that every joule of energy is delivered exactly when and where it's needed. This level of synchronization may also enable other forms of energy recovery. Landing aircraft could feed energy back into the RF network, effectively returning a portion of their kinetic energy to the system. In essence, the runway becomes both a source and a sink of energy, capable of continuously cycling power between multiple aircraft. The implications for airport design are revolutionary. Runways may no longer need to be simple strips of asphalt. They could incorporate integrated coils, sensors, and feedback systems capable of monitoring thousands of aircraft movements simultaneously. Even taxiways, gates, and aprons could serve as energy nodes, creating a fully electrified airport ecosystem. While skeptics may doubt that such a mammoth RF field could safely power a plane, Chikumbutso argues that we have only begun to explore the potential of electromagnetic energy. Conventional wisdom has long limited us to fuel, batteries, and wires, but his experiments suggest that large-scale wireless energy transfer is not only possible but scalable. In practical terms, this means airports of the future could operate independently from fuel logistics, reducing costs, emissions, and dependency on global oil markets. It could also enable more remote or underserved regions to host airports without the massive infrastructure currently required to supply aviation fuel. From a military perspective, wireless runway power could provide strategic advantages. Forward operating bases could launch aircraft without traditional fuel supplies, relying instead on portable or modular RF energy transmitters. This could make air operations faster, more flexible, and less vulnerable to supply chain disruptions. Civilians stand to benefit just as much as militaries. Airlines would gain cost savings that could translate to cheaper tickets. Passengers would enjoy cleaner, quieter, and possibly even safer flights due to reduced engine wear and reliance on combustion. The environmental benefits alone make this vision compelling. Carbon emissions from aviation are one of the fastest-growing sources of greenhouse gases, and reducing reliance on jet fuel could have a profound impact. Chikumbutso's runway RF field could become the first step toward truly sustainable air travel on a commercial scale. The technology also dovetails with other innovations, such as electric vertical takeoff aircraft, hybrid electric engines, and high-altitude energy relays. By combining these systems, we could see the emergence of an entirely new class of aircraft that never carries fuel in the conventional sense. In terms of timeline, while full-scale deployment remains a decade or more away, smaller experimental implementations may appear in private or regional airports within the next few years. Testing may begin with cargo planes or light aircraft, where regulatory hurdles and risk factors are more manageable. Once safety and efficiency are proven, scaling up to commercial passenger flights would follow, potentially revolutionizing the airline industry. Maxwell Chikumbutso's vision also challenges our understanding of infrastructure itself. Runways are no longer passive surfaces. They become active participants in energy production and distribution. The technology may extend beyond aviation to rail, road transport, and even maritime applications. Imagine electric trucks drawing power directly from highways or ships powered by electromagnetic channels in docks and harbors. The potential for global energy efficiency is staggering. Chikumbutso envisions a world where transportation and energy infrastructure are seamlessly integrated, reducing waste, lowering emissions, and increasing access to power worldwide. While many of these ideas sound like science fiction today, the principles behind them are firmly grounded in physics and early-stage experimental results. What separates Maxwell Chikumbutso from other inventors is his willingness to think on a planetary scale and to challenge assumptions that have long limited technological progress. His approach is methodical, combining theoretical physics, materials science, and advanced AI to solve problems that others consider insurmountable. In practice, a plane powered by a runway RF field would begin its journey silently. Engines would generate minimal thrust, relying on the invisible energy beneath to provide the necessary lift. Passengers would barely notice the difference, except perhaps in the quieter cabin and smoother acceleration. As the aircraft ascends, the field would taper off, transferring power seamlessly from ground-based infrastructure to onboard reserves. In this sense, the runway becomes a bridge between stationary energy sources and mobile energy demands. Chikumbutso's work also prompts us to rethink energy security. Nations could reduce dependence on imported fuel, airports could generate their own electricity, and entire fleets could operate off-grid. The environmental, economic, and strategic benefits are enormous. Yet, the challenges are equally daunting. Safety, regulatory approval, technological scalability, and public perception all remain critical hurdles to overcome. But if anyone has demonstrated the audacity and ingenuity to tackle such problems, it is Maxwell Chikumbutso. His prior inventions in self-powered vehicles, wireless energy, and RF technologies provide a roadmap for how this might be achieved. The idea of a Mammoth RF field powering commercial airplanes may seem far-fetched today. But history shows that many revolutionary ideas were once dismissed as impossible. The telegraph, the airplane, the internet, all faced skepticism before becoming integral to modern life. Chikumbutso's runway-powered flight could follow the same trajectory. In essence, this is a story of human ambition meeting the laws of physics in ways previously unimagined. It is a vision where energy flows invisibly, seamlessly, and sustainably, transforming the very way we think about movement, infrastructure, and flight. The next time you watch a plane take off, consider this. The future of aviation may not lie in bigger engines or denser fuel. It may lie beneath the tarmac, in invisible waves of energy orchestrated with precision and purpose. Maxwell Chikumbutso is building that future, one coil, one field, and one flight at a time. The runway is no longer just a strip of concrete. It is a cradle of limitless energy, ready to lift humanity into a cleaner, quieter, and more connected sky.